trying to surprise Grandpa for his 90th birthday. Surprise! Grandpa! Grandpa, are you okay?
Not my left ventricle.
We have to call 911. He's having a heart attack. Call 911.
Bobby Mays here. We just saw Grandpa suffer from his second heart attack, and now he's suffering from end-stage heart failure. His left ventricle is completely shot, but you know Bobby Mays has the fix for everything. Bobby Mays' LVAD uses state-of-the-art technology and fluid dynamics concepts to keep Grandpa going to get that heart transplant and make it to his 91st birthday. Hey, that technology stuff is none of my business. I'll pass it over to the team scientist, and he'll explain what makes this pump work.
So the LVAD, or left ventricular assist device, is used primarily in end-stage heart failure patients, mainly as a bridge to a heart transplant. So here the inlet cannula inserts into the apex of the left ventricle. All the blood in the left ventricle drains into the inlet cannula, through the pump itself into the outlet cannula, which goes up and connects to the ascending aorta. So the purpose here is to create a pressure rise from left ventricle to aorta. The pressure in a damaged left ventricle is about 5 millimeters of mercury. Ideally, we want the pressure in the ascending aorta to be about 100 millimeters of mercury. So within the pump itself, an impeller performs work on the blood and maintains flow in an axial direction. The LVAD can achieve flow rates of as high as 10 liters per minute, but its optimal operating range achieves RPMs of about 8,000 to 9,000 RPMs, which creates a pressure rise of about 80 to 100 millimeters of mercury and a flow rate of about 3 to 4 liters per minute. So really what's happening here is the impeller is giving energy to the blood and increasing the flow rate through it. And then at the exit hub right here, the diameter decreases, which basically converts kinetic energy to a static pressure, and that creates this pressure rise from left ventricle to aorta. So here we applied conservation of energy to an LVAD, and we are assuming one dimension, steady flow, constant properties across the pump, and more importantly, we're assuming no energy loss. So back up here, this is E in plus the energy provided by the pump equals E out. If you take that and you divide by volume, you get pressure energy. So here we have rho GH in plus pressure in plus rho velocity in squared over 2 plus energy of the pump equals rho GH out plus pressure out plus rho velocity out squared over 2. And then if we just rearrange that to solve for the energy of the pump, we get this equation here. And then down here we have the numbers that we pulled from literature to plug in. So the density of blood is 1,060 kilograms per meter cubed. Acceleration due to gravity, 9.81 meters per second squared. We're assuming that the height in is at 0 meters, and then we found that the length of the heart is about 1 centimeter, so we assume that the LVAD would be about 0.08 meters or 8 centimeters above the input height. And then pressure in, 5 millimeters of mercury, which converts to 666.6 pascals. Pressure out, we want 100 millimeters of mercury, which would be 13,332.2 pascals. And then V in, which we found in literature, of 1.9 meters per second, and a V out of 2 meters per second. Those were both peak values. So then if we plug those in, and we move over here, and we just crunch the numbers, we end up getting a pressure energy input by the pump of 102.8 millimeters of mercury, which, when we compare it to what we found in the literature, is fairly comparable. So the goal here with these pumps is to create a pressure rise from the injured left ventricle, which has a pressure of about 5 millimeters of mercury, to a pressure of about 100 millimeters of mercury in the aorta. And that pressure rise is developed across these pumps. So in order to achieve that very specific pressure rise, you basically alter the different properties of the pump itself. And so one important relationship in turbo machinery design and pump design specifically is the relationship between head rise and volume flow rate Q, or an HQ curve. And a very simple one can be seen here. This isn't for an LVAD, this is just for a generalized pump. So you can see as flow rate Q increases, the head rise decreases. So by altering the different properties of the pump itself, in the case of this plot, impeller diameter, you can change the HQ relationship itself. So here you can see that for an impeller diameter of 10 inches, you can achieve a higher pressure head than an impeller diameter of, say, 8 inches or 6 inches. Another important thing to note on this plot is the trade-off between efficiency and the HQ relationship. So if you're have an impeller diameter of 10 inches and you want the highest possible pressure head, you're going to be sacrificing efficiency. And then if you look at the efficiency curve, there's basically a peak where there's a point of it's called the best efficiency point. And if you want to operate at that peak efficiency, you're going to be sacrificing your pressure head. So here you can see two HQ curves for different RPMs. So if you have your pump running at a higher RPM, you'll be able to achieve a higher pressure head. The generalized relationship between pressure head and flow rate stays the same. As flow rate increases, the pressure head decreases, but you'll just be able to achieve a higher pressure head with a pump running at a higher RPM. So in this plot you can see how the relationship between efficiency, pressure head, and power and flow rate change with increasing viscosity. So basically if you increase viscosity of fluid running through the pump, you will decrease efficiency, you'll not be able to achieve as high of a pressure head, and you will need to supply the pump with more power. This isn't as pertinent to the LVAD because the blood viscosity shouldn't be changing, but it's just something that should be noted. So another property of axial flow pumps is what's known as the stator. So the impeller is the rotating component inside the pump. The stator actually sort of encases that. The stator can have a different number of vanes, and so these plots here look at the HQ relationship and the pump efficiency as a function of flow rate for different numbers of vanes. So these are based on experimental results I pulled from a research paper. So it seems as though the 7-vane case allows for the highest pump head and the highest efficiency.
Hey, thanks Dimitri. Bobby Mays, I'm back to tell you a little bit more about why Bobby Mays LVAD is the best out. We got the RPMs, blade height, number of blades, and the blade angle to keep that blood moving, keep Grandpa grooving. Okay, between these 4 pump properties, we can keep that pressure head high, make sure Grandpa doesn't die. Just for an $80,000 value. I'll tell you what, scratch that. This one time, $60,000. You call within the next 10 minutes, I'll sell you one of these for $60,000. But wait, there's more. I'll tell you what, you call in the next 5 minutes, I'll give you another one for free. That's a $60,000 value, all on me. You know,